Good morning, everybody. My name is Borja, and I'm going to talk about hydrogen embrittlement susceptibility of austenitic stainless steel obtained by SLM technique. This work is being conducted in this moment between the University of Oviedo and the Hydrogen Technologies Research Laboratory located in the University of Burgos. The laboratory, this is the start of the laboratory now. The laboratory is equipped with a high pressure, high temperature hydrogen facility, able to work up to 300 bars and 300 degrees. It's possible also to blend gases. Among others, the laboratory is equipped with a high pressure hydrogen permeation facility to evaluate trapping and the hydrogen diffusion kinetics. And we also have a hydrogen leak analyzer to determine the hydrogen concentrations. So here on the right side, we can see the outline of my talk. We are mainly focused on 316L tensile behavior, analyzed by means of ex situ and ex situ tensile tests in smooth and notch specimens. And finally, we will focus on the effect of the strain in das martensite on the embrittlement process. So regarding the introduction point, as we know, hydrogen is considered to be the best option to replace fossil fuels. However, because of its lower volumetric density, it is usually pressurized at high pressure, what can compromise the structural integrity of the materials. During the last years, we have characterized the influence of hydrogen in quench and temper martensitic steel, revealing the important influence of the nanometric vanadium carbides precipitated during the tempering treatments. So this type of strong trams plays an important role on the embrittlement process in order to alleviate hydrogen susceptibility, even increasing the yield strength without increasing the hydrogen embrittlement susceptibility. Nowadays, additive manufacturing could be considered to customize components with complex geometry, such as valves or elbows, but more studies are still needed to check if these mechanical components could be used or could be employed in hydrogen atmospheres, especially at high pressure. So this is the goal of my talk. And regarding the steel and experimental procedure, here we can see the chemical composition of the powder and the printing parameters. In this study, regarding the hydrogen precharging, we have used two different techniques. We have precharged electrochemically at room temperature with an acid solution. The pH is around 1. This current was applied during 24 hours here. And some samples were also precharged via gaseous precharging in a high-pressure hydrogen reactor following these conditions. We have two different specimens. The thin samples were used to evaluate hydrogen uptake and diffusion by means of a LICO hydrogen analyzer, and the tensile specimens with 1 millimeter thickness were used to evaluate hydrogen embrittlement susceptibility by means of smooth and notch specimens with this geometry. Here we can see the applied cross heat speed. We applied from 0.1 to 0.005 millimeter per minute, and trials were conducted at room temperature. So regarding the results, here we can see the microstructure after the SLM process. We can observe columnar austenite grains growing epitaxially along the printing direction 1. This is the position of the bed. And we have also measured the residual stresses in both directions, 1 and 2. We can observe the residual stresses is around in the range of 300 megapascals in this direction. Here in the grain interior, we can observe cellular structures with this distribution size. And here we show, so we can see the X-ray diffraction pattern. It shows that there are only Austenitic diffraction peaks. And here we are introducing the mechanical properties from left to right. Is elastic modulus, yield strength, ultimate tensile strength, deformation and reduction of area obtained in the uncharged condition after the SLM process. Based on hydrogen uptake and diffusion, 37 ppm were introduced after the electrochemical precharging, while 44 ppm were introduced after gaseous precharging. Some of the samples were exposed to air at room temperature in order to evaluate hydrogen diffusion, and by means of this curve, we can obtain the apparent diffusivity, the apparent diffusion coefficient, which corresponds to the 316L additively manufactured in this order of magnitude, 10 minus 16 square meter per second. Regarding the tensile behavior, in the case of the smooth samples, we evaluate hydrogen embrittlement susceptibility after the electrochemical left side and gaseous precharging at different cross-hit speeds. And based on these results, we can say that hydrogen indices hardening. This fact could be associated to the hydrogen dislocation pinning mechanism, and hydrogen promotes a slight loss of ductility based on deformation and reduction of area. We can see in both cases independently of the precharging methodology. Here we have represented the yield strength, ultimate tensile strength, and elongation variation as a function of the strain rate. As I mentioned previously, here we can see the hardening effect, and here the ductility drop. Regarding the fracture surfaces, dimples indicating ductile fracture were observed in the uncharged specimens without hydrogen. However, in the case of the samples precharged electrochemically, which corresponds to this speed rate corresponds to this point, this or this, we have observed like shallow dimples, which could be associated to the hydrogen-enhanced local microplasticity, which this fact explains the drop of the loss of ductility. Regarding the notch tensile samples, they were tested after the electrochemical and after the gaseous precharging at high pressure hydrogen gas. Here, or based on these results, we can see in this case, ultimate tensile strength was slightly reduced by the effect of the hydrogen atoms. Reduction of area was especially affected by hydrogen. And here we can see also that strain rate seems to play an important role on the embrittlement process, despite of the low hydrogen diffusivity, 10 minus 16 meters squared per second, obtained in this steel by means of the hydrogen desorption curve analysis. So according to this, here we have represented the ultimate tensile strength and the reduction of area as a function of the strain rate. Here we can see the embrittlement indexes obtained for the different cases. The embrittlement index indicate the drop in terms of the mechanical property. And here, regarding the fracture surfaces, we can see dimples, microvoid coalescence in the uncharged condition. However, after hydrogen precharging, we have observed dimples together with local quasi-cleavages and secondary cracks, which contribute to justify this behavior. So the point is, the strain rate seems to play an important role on hydrogen embrittlement, but why? Why? Because as we can see here, our test lasts from 33 hours to 6 hours. However, it seems, according to this behavior, hydrogen needs around 1 or 3 months to diffuse. So what is happening in the microstructure to explain, for instance, this behavior? Before testing, as we mentioned previously, our microstructure is 100% austenitic, and the apparent diffusivity is 10 minus 16 square meter per second. However, When we apply the tensile load, and because of the metastable, of the austenite metastable behavior, this austenite or martensite is formed mainly in the notch tip region, and this effect was revealed by means of the X-ray diffraction measurements. Martensite, the apparent diffusivity in the martensite phase is 4 or 5 orders magnitude higher than in the austenite phase. So by means of this effect, and also motivated by the high hydrostatic stress existing in the notch tip region, we can say that hydrogen driven by hydrostatic stress is able to diffuse through the strain-induced martensite. And by means of this, accordingly, we can explain the effect of the strain rate, which contribute to justify the loss of ductility, especially in terms of the reduction of area. Because now, during the tensile test, hydrogen is able to diffuse by means of the strain-induced martensite, which is prone to hydrogen embrittlement. So here, although this work is ongoing and we need to conduct more trials, here we present some conclusions. Regarding the smooth tensile samples, hydrogen atoms seems to induce hardening, and ductility was slightly affected. However, in the case of the notch tensile specimens, the notch tensile strength was affected by hydrogen, and the reduction of area was especially reduced in comparison to the notch tensile strength, what can be explained according to the fracture micromechanisms observed in the fracture surfaces. And it is also important to say that martensite acts as a diffusion path for hydrogen, giving rise to hydrogen embrittlement phenomena. So thank you very much for your attention.
Thank you very much, Borja, for the nice presentation. We have time for a few questions from the audience, if there are any questions. Please.
Thank you. I have one question regarding the tensile tests. For what I understood, you were comparing two things. It's both the strain rates and the hydrogen content. My question is, why did you change two things instead for example, comparing a sample with hydrogen and without hydrogen for the same strain rate?
To be honest, in this case, we have to take care with this comparison, because although I have introduced this comparison, for example, in the case of the electrochemical precharging, this precharging was conducted at room temperature. So hydrogen distribution is not homogeneous in the sample because of the low diffusivity of this steel with a face-center cubic structure. In the case of the gaseous precharging, hydrogen distribution is homogeneous. Additionally, so we have to take care with this comparison. Additionally, as you mentioned, in order to obtain the embrittlement indexes, we have to conduct trials under the same strain rate. Here, I present only the trials conducted at 0.1 millimeter per minute in the uncharged condition, but we have also tested at 0.005 millimeter per minute, and the effect without hydrogen, the mechanical properties are quite very, very similar. So in this case, we have only plotted the first points, which corresponds to 1, but as you mentioned, to obtain the embrittlement indexes, we have compared under similar strain rates. It's clear.
Any other questions? Okay, if not, we would, yes.
Sorry, just a quick question. What is the mechanism of the hydrogen going into the martensite? Is it a grain boundary diffusion, or is it?
To be honest, I don't know. We have to conduct in this moment. We have to conduct electron backscatter diffraction analysis to know if hydrogen-enhanced localized microplasticity is improved by the phase transformation or not. It's a local plasticity only in the Austenitic phase, or if it's also motivated by a phase transformation. So the point of in terms of hydrogen micromechanisms, this point is contradictory in the literature, and it's an open question in the scientific literature. It's not, it's hard to manage.
Okay, thank you.